Welcome, everyone. Ready to dive into some particle physics? Today, we're looking at anomalies. You know, those hints that maybe, just maybe, our understanding of the universe isn't quite complete.
Yeah, those bits that don't fit perfectly into the standard model.
Right, the standard model, like our physics rule book.
Hmm.
But these anomalies are like finding a few extra mysterious pages.
And they're not just theory, these are real experimental results that are, well, puzzling.
Exactly. And they can point to totally new particles and forces, stuff we haven't even imagined. It's a physics treasure hunt.
Exactly, a treasure hunt.
And a big one. We're talking about the muon's magnetic moment, that X-17 particle I keep hearing about, neutrinos, even beta decay.
It's a pretty wild ride across a huge range of scales.
So let's start with the muon. It's like the electron's heavier, more enigmatic cousin. What's the deal with its magnetic moment?
Okay, so think of the muon spinning like a tiny top.
Got it, spinning top.
Every charged particle creates a magnetic field when it spins, like a tiny bar magnet.
Okay, I'm following.
But the muon's magnetic field is stronger than expected. It's like it's spinning faster than it should.
Okay, so it's a bit of an overachiever. Why is that a problem?
Well, we have this thing called the G factor. It measures how a particle's magnetism relates to its spin. The standard model predicts a very precise G factor for the muon, and, well, we're seeing something different.
It's like the muon is playing by its own set of rules.
In a way, yes. And the big question is, what's causing this?
Yeah, what's pulling the strings, so to speak?
Some physicists think there might be particles we haven't discovered yet interacting with the muon, giving it that extra magnetic oomph.
Like invisible dance partners influencing the muon's moves.
Exactly. And these particles could be anything from lightweight Z-prime bosons to, those heavier exotic particles predicted by supersymmetry.
Supersymmetry. Isn't that where every particle has a secret twin?
You got it. Supersymmetry could explain a lot of these mysteries.
Okay, but wait, hold on. I read that even the standard model prediction for this G factor is under debate right now. Something about hadronic vacuum polarization.
Oh, yeah, that's a whole other can of worms.
Mind unpacking that one for us?
So think of the vacuum not as empty space, but a sea of these virtual particles popping in and out of existence.
Okay, getting kind of trippy here.
These particles can actually affect the muon's properties, and it makes it really hard to nail down that theoretical prediction.
So we're trying to measure the muon's spin while it's in a pool full of, like, invisible dolphins doing synchronized swimming.
That's actually a pretty good analogy. It means we need even more precise measurements and calculations to get to the bottom of this.
Well, that's one for the physics detectives. And speaking of mysteries, this X-17 particle is a big one. Some are saying it could rewrite the textbooks.
It could, yeah. The X-17 anomaly suggests there might be a brand new force-carrying particle, one we've never seen before.
A new force, as in beyond gravity and the strong and weak forces. That's huge.
It would be, yeah. A fundamental shift.
So where did this X-17 idea come from?
It started with some experiments at the Atomki lab in Hungary. They were studying nuclear reactions, at the heart of the atom.
Right deep down in there.
And they found these unexpected particle emissions.
Okay, but what's so special about these emissions? Why are they so significant?
It's all about the energy. They found electron-positron pairs shooting out at a specific energy, 17 MeV. And the energy and the angle strongly suggest that a new particle was created during the decay, and its mass would be around 17 MeV.
So that's where the name comes from. X-17, X for unknown, 17 for the energy. Sounds like something out of a sci-fi movie.
But it's real. The question is, what kind of particle is this X-17? It could be a vector boson, axial vector, or even a pseudoscalar.
Whoa, whoa, whoa. Back up for a second. Remind me, bosons. Those are...
Force-carrying particles.
Right, like photons carry light.
Exactly. So if this X-17 is a boson, it might be carrying a force we've never encountered before.
Okay, I'm starting to see the big picture here. So we've got this muon acting weird because of some potential new particle, and now this X-17 hinting at a new force.
And here's the kicker. Some physicists think those two might be connected.
Hold on, really? The muon and the X-17?
Yeah, if the X-17 interacts with muon's A and D quarks, it could explain both that weird magnetic moment and the X-17 observations.
So two separate mysteries, linked by one particle. That's incredible. And this brings us to neutrinos.
Ah, neutrinos, those ghostly particles.
Passing right through it as we speak. What's the anomaly with them? They already seem pretty strange to me.
Well, they barely interact with anything, change flavors, and might even be their own antiparticles. But some experiments are suggesting there might be even more types of neutrinos than we thought.
More types. I thought we had the electron, muon, and tau neutrinos. That's it. Right.
Well, there have been experiments where we see more electron neutrinos than expected, way more. And one explanation that's been floating around is sterile neutrinos.
Sterile neutrinos, what makes them sterile?
They would interact even less with matter than regular neutrinos. It's like if regular neutrinos are introverts, these are hermits living off the grid.
The ninjas of the particle world.
Exactly. And the reason we think they might exist is because they could explain some weird results we're seeing in neutrino oscillation experiments.
Right, neutrino oscillation,
Yes.
where they switch flavors as they travel. So are these sterile neutrinos messing with that process somehow?
They could be. It's all still very much under investigation.
Okay, so we have a muon potentially being influenced by new particles, an X17 hinting at a new force, and now sterile neutrinos potentially messing with neutrino oscillations. It's getting crowded in the particle physics world.
It's a busy place. And what's even more interesting is that these neutrino anomalies might be telling us why neutrinos have mass in the first place.
Yeah.
Something the standard model can't explain.
So these tiny, almost invisible particles could hold the key to some big questions.
Fascinating. Okay, but let's move on. Let's talk beta decay. You know, that process where a neutron decays.
Yeah, pretty straightforward, right? Yeah, neutron decays into a proton, electron, and an antineutrino. Remember learning that back in school. What's the anomaly there?
You'd think it'd be simple, but when we look at really precise measurements of beta decay, we see some discrepancies. Not big, but definitely there. Discrepancies from what the standard model predicts.
So tiny deviations, big implications.
Exactly. One possibility is that it challenges the unitarity of the CKM matrix.
The CKM matrix. Now we're getting
Oh.
technical.
It's basically a way to describe how quarks mix and interact, and it ensures probability is conserved. But if it's not perfectly unitary, well, it implies there are missing pieces in our model.
Missing pieces, like what?
Some theorists suggest new particles, things like W' bosons or leptoquarks. They could subtly change the rates of beta decay.
W' bosons, leptoquarks.
Yeah,
It's like we're constantly adding characters to this particle physics story.
we are. It never gets boring.
Okay, so maybe beta decay isn't so simple after all.
Not quite. And on top of that, there's another puzzle, the difference between how we measure neutron lifetime in beam versus bottle experiments.
Beam versus bottle. Intrigued. Tell me more.
Okay, so in bottle experiments, you trap neutrons and see how long they take to decay.
Makes sense.
Beam experiments measure the decay products, like those protons, to figure out the neutron's lifetime.
Got it. Two different ways of measuring the same thing.
Right, but they give slightly different results. And that difference, even though small, hints that we might be missing something fundamental about how neutrons decay. Maybe there are undiscovered decay pathways.
Wow. So much complexity in something that seems so simple. It's like every time we think we understand something, there's another layer to uncover.
And speaking of layers, let's talk about B mesons. They're full of surprises, especially when they decay.
Beam essence. Okay, remind me about those.
B mesons, they're particles made of a bottom quark and an antiquark. And their decays often involve the weak force, which, as we know, can be a bit quirky when it comes to symmetry.
Okay, when you say symmetry, do you mean like how a snowflake looks the same when you turn it?
Sort of. We're talking about fundamental symmetries in physics. One of them is CP symmetry, and it basically says physics should be the same if you swap particles for antiparticles in flip space.
That sounds pretty fundamental. What's the anomaly with these B mesons?
Well, we've seen some of their decay patterns violate CP symmetry, which is rare in the standard model, really rare, and that suggests there might be something else influencing these decays, something beyond our current understanding.
Wow, so it's like these B mesons are rebelling against the laws of physics.
Maybe. But more likely, they're revealing a deeper layer of those laws.
A secret code we haven't cracked yet.
Exactly.
So what are we doing to crack that code?
Experiments like Bell II and LHCb are giving us lots of new data. We're learning more all the time.
So with B mesons, it's like they're giving us glimpses of the rule book, but it's in a language we're still trying to learn.
A great way to put it.
Okay, but this is a lot to take in. Let's talk scale for a second. We're talking about things so tiny and at such high energies.
It is mind-boggling.
Imagine trying to weigh atoms. And now imagine trying to weigh fundamental particles like the W boson.
And we've actually managed to measure the W boson's mass very precisely thanks to experiments like CDF.
That's impressive. So what's the issue then?
The issue is That measured mass is heavier than the standard model predicts. Like, a lot heavier. 7 sigma heavier.
7 sigma, that's statistically huge, right?
It is, and it suggests there's something fundamentally wrong with our understanding of the electroweak theory.
Of the electroweak theory, that's the one that unifies electromagnetism and the weak force, right?
That's the one.
Yeah.
And this W boson is throwing a wrench into the works.
So is this the end of the standard model as we know it?
Well, maybe not the end, but definitely a sign we need to rethink some things.
So the W boson is flexing its muscles, making us question our understanding of the universe.
You could say that.
Yeah.
And it's exciting. It pushes us to refine our theories and experiments. Who knows what we might discover?
It's a wild ride for sure. We've got muons, a potential new force, neutrinos, and now a heavyweight W boson shaking things up. This is getting good.
And we're just getting started.
It feels like we're uncovering layer after layer, and with each layer, more questions.
That's science for you. The more we learn, the more we realize we don't know. But hey, plenty more to explore. Let's talk about the LHC, the Large Hadron Collider.
Ah, the LHC,
Yeah.
where they smash protons together at incredible speeds.
Exactly. And it's giving us glimpses of things we can't explain with the standard model alone.
Ooh,
Like these multi-lepton anomalies.
multi-lepton anomalies. Okay, break that down for me.
So leptons, those are particles like electrons, muons, and tabus.
Right, those guys.
In certain collisions at the LHC, we're seeing more leptons than we should. Way more.
Like the LHC is spitting out extra particles.
Yeah, in specific configurations it is, and some of these deviations are significant, exceeding 5 sigma.
5 sigma, that's the gold standard, right? Statistically speaking, it's a big deal.
It is. And it's not just random. Some of these events have what we call Higgs-like signatures.
Higgs-like, as in the Higgs boson, the one that gives everything mass.
The one and only. And the way these leptons are showing up, it resembles how the Higgs boson decays.
Interesting. So are we saying there could be more Higgs bosons out there, like a whole family?
It's possible. But it gets even more interesting. There are different kinds of these multi-lepton events. Some have 2 opposite sign leptons and B jets, those sprays of particles from bottom quarks. Others have 2 same sign leptons, and some even have 3.
So it's not just about the extra leptons, it's the specific patterns they're showing up in, each one telling a different story.
Exactly. And untangling those stories is a challenge. We need to be absolutely sure these aren't just flukes.
Right, got to rule out all the usual suspects before we go claiming new physics.
Exactly. We need to model the standard model background very carefully, make sure there's no other explanation.
Okay, let's say we've done that. We're sure it's something new. What could it be?
Well, there are a few possibilities. One is that there are new particles being produced, and they're decaying into these leptons. Could be anything from supersymmetric particles to, heavy neutrinos.
Supersymmetry, heavy neutrinos. They're popping up everywhere.
They are popular candidates. Another possibility is new forces, mediated by particles like Z-prime bosons. They could be preferentially decaying into leptons.
So these Z-prime bosons are like the lepton whisperers, influencing their behavior.
I like that analogy. And as the LHC keeps collecting data, we're bound to learn more.
Can't wait to see what they find. Okay, but the LHC isn't just about finding particles. There are also those resonances.
Ah, yes, resonances. Bumps in the data that signal the creation of new particles.
It's like tuning a radio and hitting a strong signal.
Perfect analogy. And at the LHC, physicists are always looking for those signals. And guess what? They found some interesting ones.
Ooh, spill the tea. What kind of signals?
Well, one is at 95 GeV, and it's shown up in both diphoton and d-tau data.
So 2 photons or 2 tau leptons. Why is that a big deal?
Because it suggests a new particle. And some think it could be another Higgs boson, a lighter one than the one we already know.
Wow, so a whole Higgs family. That's wild. Are there other signals?
There are. Another interesting one is at 152 GeV, and it's showing up with what we call missing energy.
Missing energy. Sounds spooky. What does that mean?
It means particles are being produced that we can't directly detect. Could be weakly interacting particles like neutrinos or, something entirely new.
So this 152 GeV signal is like a ghost, hinting at something we can't see.
Exactly. A strong hint of new physics. And the LHC keeps looking. More data will tell us more.
So many mysteries. Okay, but we've been talking a lot about particles. What about the strong force, the one that binds quarks together? What's happening there?
The strong force is a beast. We're still figuring it out. One way to study it is to look at these dijet events, where 2 jets of particles spray out in opposite directions.
Like 2 fire hoses, but spraying particles instead of water.
I love that. And by studying those dijets, we can look for signs of new particles that interact via the strong force. And we've seen something interesting, a dijet resonance around 950 GeV.
Another resonance, but this one involving jets. What's so special about it?
Some physicists think it could be diquarks, hypothetical particles made of two quarks bound together.
Diquarks. It's like a double-stuffed Oreo of the particle world.
You got it. If diquarks exist, it would change our understanding of the strong force.
So a whole new chapter in the story of the strong force.
Right. But there's a catch. Measuring jets is messy. It's hard to be precise about their energy and momentum, so pinning down the nature of these dijet resonances is tricky.
Some more data needed.
Always. But it's a fascinating possibility.
It seems like everywhere we look, there's a hint of something new.
It's an exciting time. It shows how powerful our experiments and theories are becoming. We're pushing the boundaries.
Let's push them further. We've talked about anomalies at the heart of atoms at the TeV scale, but what about the really high energy frontier? What's happening there?
Now that's where things get interesting. At the highest energies the LHC can reach, we're probing the very fabric of reality. But even then, some particles are too heavy for us to create directly.
So how do we even look for them? It's like trying to study a shadow without knowing what cast it.
That's a great way to put it. We have to look for subtle deviations in the way known particles behave at these energies, like trying to see a hidden object by how it distorts light passing through a curtain.
So these heavy particles are like ghosts, leaving their mark even though we can't see them.
Exactly. And one place these distortions can show up is in the high-energy tail of certain distributions, especially in dielectron events, where we see pairs of leptons, like electron-positron pairs.
Okay, so these hidden particles are like giving these dileptons an extra energy boost.
Exactly. And guess what? Both ATLAS and CMS, those two big detectors at the LHC, they've seen an excess of these dielectron events at really high energies.
Okay, another hint of new physics. This is getting good.
It could be. We need more data, but this could be a sign of particles at the 10 TeV scale.
10 TeV. That's crazy high energy.
It is, and it hints at something particularly intriguing. Lepton flavor universality violation.
Lepton flavor universality violation. That's a mouthful. What does that even mean?
It means that electrons and muons, though similar in many ways, might not behave identically at these extreme energies.
Like different rules for different leptons. But why would that be?
That's what we're trying to figure out. This excess suggests there might be forces or interactions that prefer electrons over muons.
Like electrons have a secret handshake that muons aren't in on.
Exactly. And those secret handshakes might be happening through new particles, like heavy Z-prime bosons or leptoquarks.
Z-prime bosons and leptoquarks, they keep coming back. So what's the next step?
More data from the LHC, that's how we'll confirm or refute these hints. It's an exciting time.
I'm on the edge of my seat. Okay, we've got all these potential new particles, Z-primes, W-primes, leptoquarks, supersymmetric particles. It's a lot. How do we make sense of it all?
It is a lot. One way is to group them by their properties, how they interact with the standard model.
Okay, so those bosons, the force carriers, we've got Z-primes, W-primes, and that X17. What's the common thread?
They all suggest new fundamental forces, beyond the four we know: gravity, electromagnetism, and the strong and weak forces.
New forces? That's crazy. What would they even do?
We can only imagine. They might influence particles in ways we haven't even thought of. Dark matter, dark energy, the early universe, galaxy formation. Who knows?
The possibilities are endless. Okay, what about those quarks, the leptoquarks and diquarks? What's the deal with them?
Leptoquarks are interesting. They could connect quarks and leptons, maybe even unify those two fundamental families.
Like the peacemakers of the particle world.
Exactly. A big step towards some more fundamental theory. And diquarks, well, they could show us new things about the strong force, add another layer to how we understand matter.
And neutrinos. Both the regular ones and those mysterious sterile neutrinos.
Regular neutrinos are weird enough with their flavor-changing ways, but sterile neutrinos, those could explain why neutrinos have mass, something the standard model can't handle.
So the sterile ones are like the silent partners, pulling the strings behind the scenes.
That's a great way to think about it, and their existence could have huge implications for cosmology.
Okay, last one, and I'm ready for my mind to be blown. Supersymmetry.
Ah, SUA. The idea is every particle has a supersymmetric partner particle, like a mirror universe of particles.
A mirror universe. That means double the particles.
Yep. Might seem complicated, but CUSY solves a lot of problems. For example, it could explain why the Higgs boson is so light.
The hierarchy problem. Right, the Higgs mass should be huge, but it's not.
Exactly. CUY could fix that. Because the contributions from the supersymmetric particles would cancel out the contributions from the standard model particles, stabilizing the Higgs mass.
So it's like a cosmic balancing act.
Perfect analogy. And that's not all. CSY could also provide a candidate for dark matter,
Dark matter, that invisible stuff that makes up most of the matter in the universe.
the one and only. CUSY predicts a particle, the LSP, that's stable and weakly interacting, just like dark matter should be.
Two birds, one supersymmetric stone. Amazing. And you're saying some of these anomalies we've talked about could be hints of CZY.
They could be. The muon G2 anomaly, those multi-lepton anomalies, all potentially explained by CZY. It's an exciting avenue we're exploring.
Okay, so many potential new particles, new forces, even a mirror universe. Is there some kind of theory that can explain it all?
That's the ultimate goal. A theory of everything, a TOE. That explains all the fundamental building blocks and how they interact.
A theory of everything. Are we anywhere close?
We're working on it. The standard model has been incredibly successful, but it's clearly not the whole story. It doesn't explain dark matter, dark energy, neutrino masses, or why gravity is so weak.
So these anomalies, these missing pieces, could they be the key to finding that TOE?
They might be. They're like clues, telling us there's more to discover. They're guiding us toward a deeper understanding.
It's a fascinating journey. But do you see any patterns emerging? Any connections between these seemingly separate puzzles?
That's what we're trying to figure out. One example is the possible connection between the muon G2 anomaly and that X17 particle.
Right. The X17 could interact with both muons and quarks, potentially explaining both mysteries.
Exactly. If true, it would be a big step towards simplifying our understanding.
Like finding a secret passage connecting two different rooms in a mansion.
Love it. And there might be other secret passages out there. Some theories suggest a link between the muon G2 anomaly and the B mesonin decay anomalies.
So multiple anomalies could point to the same underlying new physics, like different symptoms of the same disease.
Precisely. That's why we need to look for those patterns and connections. It's what we do, both experimentally and theoretically.
This is so cool. But where do we go from here? What are the next steps?
The journey continues. Experimentally, we need more data, better techniques. The LHC is getting upgrades to increase its luminosity, the rate of collisions, so we can see rarer events, heavier particles.
The LHC is getting a power-up. Awesome. And what about new colliders? Anything on the horizon?
There is. The Future Circular Collider, the FCC, is on the drawing board. It would be almost 100 kilometers around, colliding particles at energies way beyond the LHC.
Wow, a supersized LHC. But even with all that, we need theory too, right?
Absolutely. We need new frameworks to make sense of the data. Some extend the standard model, others are more radical.
So we're exploring new territory, needing better maps and better tools.
Exactly. And the interplay between theory and experiment is key. They push each other forward.
Scientific dance.
Yeah.
But let me ask you, given all these anomalies, do you think we're really seeing signs of new physics, or are these just flukes that will disappear with more data?
That's the big question. We have to be cautious. Need more data, more analysis before we can claim new physics for sure.
Extraordinary claims require extraordinary evidence.
Exactly. But I'm optimistic. These anomalies have been around for a while, showing up in multiple experiments. Hard to ignore them.
So are we maybe, just maybe, on the cusp of a revolution in physics?
It's possible. These anomalies are cracks in the foundation. They could herald a whole new era in our understanding.
And what might that new era look like? What are the leading candidates for a new framework?
Supersymmetry is a strong contender. It's elegant, solves problems, and could unify forces and explain dark matter. Then there are extra dimensions, where our universe is just one slice of a higher dimensional reality. And of course, string theory, where everything is made of tiny vibrating strings.
So many possibilities. How do we choose?
We explore them all, test them rigorously. That's the scientific method in action. Each framework has its strengths and weaknesses, its predictions. We see what holds up.
So it's like a cosmic competition. But with all these theoretical options, how do we even test them?
That's where experimental ingenuity comes in. We need new experiments, new colliders, new analysis techniques. It's a challenge, but it's driving innovation.
So these anomalies are not just theoretical curiosities, they're shaping the future of physics.
Exactly. They're beacons guiding us toward a deeper understanding, and the journey is just beginning.
I love that. But let's take a moment to acknowledge the human side of this. It takes a lot of creativity, ingenuity, and collaboration to make these discoveries.
You're absolutely right. Particle physics is a global effort, thousands of scientists working together.
It's like a symphony orchestra, each scientist playing a different instrument.
Beautiful analogy. And like an orchestra, it takes dedication and teamwork to create something truly amazing. And the rewards are huge. Those moments of discovery, seeing a pattern in the data, that makes it all worthwhile.
So it's not just about the data, it's about the human spirit of exploration.
Exactly. And the drive to understand our place in the cosmos.
Well said. But these grand experiments aren't cheap. How do we justify the costs to the public?
It's an important question. We have to communicate the value of fundamental research, show that it benefits society.
How do we do that? How do we show people it's worth investing in?
We can highlight the technological spin-offs. The World Wide Web, for example, was invented at CERN. It was meant for physicists to communicate, but look at it now.
Right. The internet. Born out of particle physics. What else?
Medical imaging, like PET scans, rely on particle physics technology, and advances in computing, data storage, all driven by particle physics.
So it's like planting seeds that grow into a forest of innovation.
Exactly. But beyond that, there's the value of knowledge itself, understanding our place in the universe.
It's about pushing the boundaries of what's possible, both intellectually and technologically.
Exactly. And these anomalies, these cracks in our understanding, they're invitations to explore, to dream big.
Okay, but let's get specific for a second. That W boson mass anomaly. 7 sigma deviation. That's huge.
It is a major red flag. It tells us there's something we're missing in our theories.
Are we talking a breakdown of the standard model?
Maybe. It's too early to say for sure, but we're taking it seriously. If it's true, it has big consequences for the electroweak force.
And that force governs things like beta decay, nuclear fusion, the stuff that powers stars.
Exactly. So a misunderstanding there could have ripple effects across physics.
Okay, so what are the possible explanations?
New particles could be interacting with the W boson, changing its mass. Supersymmetric particles, maybe, or something totally new.
And the Higgs mechanism, the thing that gives particles mass in the first place, could that be involved?
Absolutely. The Higgs mechanism might be more complicated than we thought. Maybe new particles or interactions are affecting the W boson mass. And some theories even link this to other anomalies, like the muon G2.
So it's like a domino effect, one anomaly leading to another.
Exactly. And that's why the W boson mass anomaly is so important. It could be a key that unlocks other mysteries.
Let's talk about those multi-lepton anomalies. So many different signatures, potential explanations. Are any theories gaining traction?
It is a bit of a kaleidoscope, isn't it? But
Yeah.
that's what makes it exciting. And yes, some theories are standing out. Supersymmetry, for example, it predicts the production of multiple leptons. So these anomalies could be a good sign for Cesius Y.
But we haven't found any supersymmetric particles yet, right?
Not yet. Maybe they're heavier than we can currently see. Or maybe they're hiding in plain sight. Their decays making them hard to spot.
So the hunt continues. Any other explanations for those multi-lepton anomalies?
Heavy neutrinos could be a factor. They'd be hard to detect directly, but their decays could make those extra leptons. And they could help explain why regular neutrinos have mass. And of course, we can't forget about Z-prime bosons and leptoquarks.
Those guys again. So what's the bottom line?
The multi-lepton anomalies are a hotbed of possibilities, a very active area of research.
Okay, so SUSY, heavy neutrinos, Z-primes, leptoquarks, all on the table. Let's shift gears back to those resonance signals. We talked about the 95 GV and 152 GV ones. Anything else interesting popping up?
Always. The LHC is full of data. One intriguing signal is around 680 GV.
680 GV, that's pretty heavy. Why is that one special?
It's showing up in multiple channels, diphoton, DZ boson, even di-Higgs events.
So this 680 GV particle is like the social butterfly of the particle world, interacting with everyone.
I like that. And seeing it in multiple channels makes it more believable. Some even think it could be another Higgs boson, an even heavier one.
The Higgs party keeps growing. And what about those dijet events? We talked about that 950 GV signal and diquarks. Anything else there?
There's always something. One signal is around 3 TeV, a real heavyweight. And it seems to be connected to tau quarks. Those are the heaviest quarks we know. Suggests a link to new physics that likes heavy particles.
An exclusive club for the heavy hitters. It sounds like the strong force is still full of surprises.
It is. We're just scratching the surface.
With all these signals and new particles, it seems like the standard model is showing its limits. Is it time for a complete overhaul?
The standard model has been incredibly successful, but it's not the end of the story. These anomalies are cracks in its foundation. Whether it needs a total makeover or just some serious renovations, that's the question.
Like renovating a house, but not sure if we need to knock down walls or just add some rooms.
Perfect analogy. The standard model is a solid foundation, but we might need to expand on it.
So exciting times. But let's go back to that muon G2 anomaly. It's been around for a while, right?
The muon G2, a classic. It's been puzzling us for decades. A tiny crack that hints at something deeper.
And that crack is becoming more and more noticeable, right?
It is. The discrepancy between theory and experiment keeps getting stronger. New experiments are planned to get even more precise measurements.
Getting a closer look at that crack, hoping it reveals a new world.
Exactly. Precision experiments are powerful. Sometimes the smallest deviations lead to the biggest discoveries.
What about neutrinos? Any other mysteries there besides sterile and heavy neutrinos?
Oh, the neutrino world is always bustling. One puzzle is the reactor antineutrino anomaly. We're seeing fewer antineutrinos from reactors than expected, and sterile neutrinos could explain that.
So they're like neutrino thieves, making them disappear.
Haha, in a way, it's an active area of research for sure.
So many mysteries. It's amazing to think about the implications of all this. We're talking about the fundamental building blocks of the universe. Quarks, leptons, bosons, the forces, maybe even space and time.
It's a revolutionary time for physics. These anomalies are making us rethink what we thought we knew.
Are we on the verge of a paradigm shift?
Maybe. These cracks in the foundation could lead to a whole new scientific revolution.
And what might that revelation look like? What are the leading candidates?
Well, supersymmetry is a strong contender. Extra dimensions are another possibility. And of course, there's string theory.
So many possibilities. How do we even choose?
We explore them all, test them rigorously. Each one has its strengths and weaknesses. We see which one survives the scrutiny.
A cosmic competition. But with all these theoretical options, how do we test them experimentally?
That's where the creativity of experimental physics shines. We need new experiments, new colliders, new ways to analyze data. It's a challenge, but a thrilling one.
So these anomalies are more than just theoretical puzzles. They're shaping the future of physics.
Exactly. They're beacons leading us toward a deeper understanding.
I love that. But before we go, let's appreciate the human element of all this. It takes a lot of hard work and collaboration to make these discoveries.
Absolutely. Thousands of scientists working together from all over the world.
It's like a symphony orchestra, each playing their part.
Beautiful analogy. It takes years of practice, dedication, and teamwork. But those moments of discovery when we see a new pattern, it's all worth it.
So it's not just about the data, it's about the human spirit of exploration.
Exactly. The drive to understand our place in the universe.
Well said. But these big experiments aren't cheap. How do we explain the value of this research to the public?
It's important to communicate that value. Fundamental research benefits society in many ways.
How do we make that case? How do we show people that it's worth investing in?
We can highlight the technological spin-offs. The World Wide Web, for instance, invented at CERN to help physicists communicate, and look at the impact it's had.
The internet, born out of particle physics. Amazing. Are there other examples?
Tons. Medical imaging, like PET scans, advancements in computing and data storage, all thanks to particle physics.
It's like planting seeds that grow into a forest of innovation.
Exactly. And beyond the practical benefits, there's the value of knowledge itself, expanding human understanding, exploring our place in the cosmos.
So we're pushing the boundaries of what's possible, both intellectually and technologically.
Precisely. Particle physics is all about curiosity, ingenuity, and the pursuit of knowledge. And these anomalies, these hints of something new, they're invitations to explore, to question, to dream big.
Let's talk about the muon G2 anomaly. It's been around for a long time.
The muon G2, it's a classic, a tiny crack that hints at something deeper.
And that crack seems to be widening with each new measurement, right?
It is. The discrepancy between theory and experiment keeps getting stronger. New experiments are being planned to get even more precise measurements.
So we're getting a closer look at that crack, hoping it reveals a whole new world.
Exactly. Precision experiments are powerful. Sometimes the smallest deviations lead to the biggest discoveries.
Now, what about neutrinos? Are there any other neutrino puzzles besides sterile and heavy neutrinos?
Oh, the neutrino world is always bustling. One puzzle is the reactor antineutrino anomaly. We're seeing fewer antineutrinos from reactors than expected, and sterile neutrinos could explain that.
So they're like neutrino thieves, making them disappear.
Haha, in a way, it's an active area of research for sure.
Wow, so many mysteries. It's amazing to think about the implications of all this. We're talking about the fundamental building blocks of the universe. Quarks, leptons, bosons, the forces. maybe even space and time.
It's a revolutionary time for physics. These anomalies are making us rethink what we thought we knew about the universe.
Are we on the verge of a paradigm shift?
Maybe. These cracks in the foundation could lead to a whole new scientific revolution.
And what might that revolution look like? What are the leading candidates?
Well, supersymmetry is a strong contender. Extra dimensions are another intriguing possibility. And of course, there's string theory, where everything is made of tiny vibrating strings.
So many possibilities. How do we choose?
We explore them all, test them rigorously. Each one has its strengths and weaknesses, its predictions. We see what holds up.
A cosmic competition. But with all these theoretical options, how do we even test them?
That's where the creativity of experimental physics shines. We need new experiments, new colliders, new ways to analyze data. It's a challenge, but a thrilling one.
So these anomalies are more than just theoretical curiosities. They're shaping the future of physics.
Exactly. They're beacons leading us toward a deeper understanding. And the journey is just beginning. The first takeaway is that the Standard Model, as successful as it's been, it's not the whole story. There are things we're seeing, pieces that just don't fit, and they suggest there's more to discover. A deeper level of reality, maybe?
Right, like our map of the universe is good, but we're starting to see the edges, the places where we need to explore more.
Exactly. And these anomalies, they're like our compasses and telescopes pointing us in the right direction.
And these anomalies, they're also different. Different energy scales, different particles, different forces.
Absolutely. There's no single answer. It's not a one-size-fits-all situation. We might be looking at multiple layers of new physics, each with its own set of rules, operating at different scales.
Like exploring a massive dungeon, each level with its own challenges and treasures.
I love that. A perfect analogy. And the final takeaway, maybe the most important one, is this. We are living in a golden age of discovery. These anomalies are giving us clues like never before, and the tools we have, the techniques we're developing, they're opening up amazing new possibilities.
So it's a pretty incredible time to be a particle physicist.
Yeah.
Or even just someone who loves to think about the universe and how it all works.
It is. There's this feeling in the air, a sense of anticipation, like we're on the verge of something big, something truly groundbreaking.
Before we finish up, I have to ask, given everything we've talked about, what do you think the future holds for particle physics? Will we see the Standard Model completely overthrown, replaced with a new theory? Or will it be more of a gradual evolution and upgrade?
That's the big question, isn't it? It's hard to predict the future. Science is full of surprises. But if I had to guess, I'd say it'll probably be a mix of both. We'll likely have some major breakthroughs that make us rethink some fundamental ideas. But the Standard Model has been so successful, it's hard to imagine it just disappearing completely.
So like building a new house, but keeping some of the good bricks from the old one.
Exactly. The Standard Model is a great foundation, but we need to keep building, adding new rooms, new floors to fit all the new knowledge we're gaining about the universe.
And how long do you think it will be before we see some of these big discoveries? Years, decades, longer.
It's hard to put a timeline on it, but with the LHC, with all the upgrades and the possibility of new colliders like that FCC, I think it's realistic to think we'll see some major discoveries within the next couple of decades.
So exciting times ahead. But before we let everyone go, let's take a moment to appreciate the sheer scale of what we've been discussing. These particles, these forces, these energies, they're so far removed from our everyday experience, it's almost impossible to grasp.
It really is. It's amazing to think about what we've accomplished. We've built these incredible machines, like the LHC, that can recreate the conditions of the early universe. We've developed these mind-blowing theories that explain how particles behave with amazing accuracy. And we're still pushing, still searching for deeper answers.
And it's not just about the universe out there, it's about us too, isn't it?
Yeah.
Our capacity for curiosity, for creativity, for working together to solve these incredible puzzles.
Exactly. Science is a human endeavor. And these anomalies, these mysteries we've been talking about, they're not just scientific problems to solve, they're invitations. Invitations to explore, to question, to dream.
Well said. So to everyone listening, keep asking those questions, keep exploring, and never stop being curious about the universe. You never know. You might be the one to make the next big discovery.
And remember, the universe is vast and full of wonder. We've only just begun to scratch the surface. So keep exploring, keep questioning, keep wondering. The journey is just beginning.
Thank you for joining us on this incredible deep dive into the world of particle physics anomalies. It's been a fascinating conversation.
Until next time, keep looking up and keep asking why.